This is our third and last homework for Chapter 5. We deliberately ended in section 5.2 because the Romberg integration is really the culmination of our integrators. You can kind of see that by the requirements we're giving it. We want to have an error of 10 to the minus 12th or less. For the trapezoid rule, we only required 10 to the minus 4th. For the Simpson's rule, we required 10 to the minus 8th, but we're requiring an error of less than 10 to the minus 12th for the Romberg integrator. Part of your job, this homework, will be to compare those three orders relative to the number of iterations it takes for all three. Okay, so problem 1 is going to be given to you, so that's not worth points, but if you study that, you'll be able to do part B a whole lot easier. And so part A is to review the pseudocode that I'm providing you. So you don't need to write it yourself. You can just take mine and review it. And take a look carefully at how it works, and then move to part B, which will be to write a MATLAB script that will be able to implement the pseudocode that we have in part A. So you're going to get 15 points to create the R matrix. And recall from our lectures, you're developing a triangular array where you can look at the first order solution, second order solution, third order solution, and so forth. I want you to look at relative error in two ways. The first way is to look at the last two diagonal entries going down that R matrix. View the very last one as your most precise number and the second to last one as your next best number, and do the relative error like we have in the past using those two values. I also want you to compare the lower right hand corner of the R matrix to the exact result you got when you did the integral exactly theoretically. So that's going to be most of the points. I do want you to iterate until this last error, the R of nn1, falls below the required tolerance. There's our tolerance, 10 to the minus 12th. So to stop the algorithm, you'll just use the second relative error. And once it gets below 10 to the minus 12th, you can quit. Okay, finally, I want you to take a look at how many cycles did it require to do this Romberg integration. In other words, how many times did it go through its major loop, and compare that with how many times it took the trapezoidal method at 10 to the minus 4th to be able to achieve its requirement, how long it took for the Simpson's rule to hit 10 to the minus 8th, and you're going to compare those two iterations with how long it takes the Romberg integration to hit 10 to the minus 12th using this relative error as a stopping point. And I think you'll be surprised at the result of that. Okay, so let's go ahead and put in some hints to help you get started. Really, you go back to the method in 5.1. That was our trapezoidal rule, because the Romberg method is really just linear combinations of the trapezoidal rule. Your Romberg algorithm in the book, and also one that I support here, is a zero indexed algorithm. So don't forget that your MATLAB language is one index. Things start with 1, but your algorithms tend to start with 0. So you've got to be a little careful with making sure you offset that by 1. You start off, just like with the trapezoidal rule, with the full interval from B to A. That's going to be your H. You initialized your counter to be 0, and you will have to set up your R matrix to be a 10 by 10 matrix. That'll be plenty of space. You shouldn't use it all. If you use more than that, something's gone wrong. You start off with your upper left-hand corner of your R matrix as being the function evaluated at each endpoint, added together and divided by 2. So you're taking the average times H. Well, that was just our very macro trapezoidal rule when we made one trapezoid out of the entire interval. We store that in R of 0, 0. Okay, so you need to now set up a master while loop. That will be your outer loop, and you will terminate that loop once your relative error gets below the threshold of 10 to the minus 12th. So these are the steps you need to do. You will increment n and cut the H value in half as the first thing you do within your while loop. So that's not hard, just go ahead and do that. So let's take a look at step 2. We're going to have to create the 0th column of the R array using this formula. Now what we're doing with the formula is we are dropping straight down the left column, and we're taking whatever we had before and using that plus a little more calculations to develop the next row down, but still in column 0. Now what you don't do, and this will be a little tricky, you don't do what the book did, and that is to try to fill that whole column first, because this method is going to require you to iterate and check as you iterate to see if you've met your relative error requirement. So if I go back to how the book did it for a moment, what the book does is it takes the R00 value, which you already have, so n is now 1, that means you're trying to build the first row, and you go back and say, well, I know what R00 was, I divide it in half, and now I have to add on some other terms. Well, what are the other terms? Well, my n is 1, so n minus 1 is 0, 2 to the 0 is 1, so I'm summing from k equals 1 to 1. Well, that just means you're going to get one value. Okay, that's not hard. Let's see what the value is. I put in k equal to 1. 2 times k is 2. 2 minus 1 is 1, which means I am moving up a value of h from a. Now remember, we already cut h in half, so h is at the halfway point between a and b. So we evaluate that function, which has not been evaluated yet, multiply it by this new value of h that's been cut in half, and just add it to 1/2 of what I had in R00, and that becomes R10. No problem. Now what the book wants you to do is just keep doing this down column 0. So it says, well, now that you know R of 10, let's let n equal 2. So R of 2 minus 1, 0, which is R of 1, 0. And now we take a new sum from k equals 1 to 2 to the 2 minus 1. Well, 2 minus 1 is 1, 2 to the first power is 2, which means we're just adding up 2 new values. H was cut in half again, because every time I go through the loop, I've got to cut h in half. And let's see which 2 values I get. Well, I get 2 times 1, k is now 1, minus 1. So I'm taking 1 times h, but h has been cut in half. H is now 1/4 what it was to start with. And so I'm moving up from a plus 1/4 of the original h. Well, that value has never been evaluated before. In fact, it's exactly halfway between the starting point and the midpoint. And I'm going to get another one, which is halfway between the middle and the final point, b. Let's check that. K is now 2. So I take 2 times 2 is 4, minus 1 is 3. So I'm taking 3 times the h, which is 1/4 of that of the original value. So that must mean I'm at the 3/4 point between a and b. Add those two up, multiply by this new h, which is 1/4 the original value, add it to r of 10, divide it in half, and I get an r of 20. So the book has you just doing that in a big loop. Now, I am going to have you do that too, but each time you do that, you're also going to build to the right using the next formula that you're going to see down below, because I want each row computed fully before you move on to the next row. The reason for that is I want you to check the relative error each time that you complete a row. Now we have step 3, and step 3, like we said before, is going to be done concurrently with step 2, and you now have to develop each column of whatever row that you're on. Okay, that formula looks complicated, but it's not that hard to program. So just put this in the way it is. You already know what the n is because you're on a particular row, and you're going to have to do each m until m gets up to n. So on your very first, your 0th calculation, you have nothing to do. You've already calculated. On row 1, you're going to have one of these calculations to do. When you get to row 2, then you'll have 2 of these calculations to do, and so forth. So you're going to go through and do this formula, just plug it in, calculate it, and that will fill up the rest of the R array. At the end of that loop, then that is when you need to check for relative error to see if you have dropped below the 10 to the minus 12th requirement. So your M does loop from 1 to N on this inner for loop. Page 219, again, this is just a little warning that your algorithm that's in the book wants you to come down that first column first, and I do not want you to do that because you cannot check your relative error if you do it the way the book does. So we're taking a little bit of a twist here. Here is the actual pseudocode that you're going to use. This is your initialization step. Here you define your tolerance, set your relative error to be something big, and initialize a counter, which we will call N. Here's your master loop, this while loop right here. And here's where you start incrementing your N and cutting your H in half and starting a new sum. The S is going to be the variable that stores that sum that we saw in the prior slides. Now again, just like we did before, we're going to allow X to be backed off by a value of H, which note has already been cut in half. And that's convenient because then we can increment X by 2H, which will skip over all the values that we've already calculated and only leave us with those that need to be calculated for that sum. So it's a little bit more efficient way than the math that we have set up. We then calculate our function evaluated at X. Now what's our function? Well, it's the function that we're using, which is the sine of 2x or 2 sine cos x, whichever you prefer on that case. And we start accumulating those values. Then you build your column. That's your column formula. That was what we called step 1. And here's the inner loop where you compute all the other entries in the same row that you're on in the K loop. Okay, so that then when it's all done, you need to come down and ask yourself if you've met your relative error requirements or not. Now, if you're on your first pass, you can't compute a relative error. You need at least 2 steps before you can. So this is just a check to make sure that you're not on the first step. And if not, then here's your relative error calculation that you can code up. So take a close look at this P code. You can develop your MATLAB right from it and be able to get a successful computation from that and see how you do. So let's just review that. We've already seen this list before when we got started, but your job is really to start with part B. Part A we've now done. And you're to print out the R matrix. You're to print out the relative error 2 ways using the last 2 diagonal entries of R, and then using the very lower right-hand corner of R relative to the exact result that you got out of the theoretical integral. Okay, remember to iterate until the tolerance is met based on this relative error in part 2. And then finally, look at the number of cycles that you had in the trapezoidal rule, that was homework 5.1, in the Simpson's rule, which was 5.3, and finally this one, which is 5.2. And remember, you were only iterating to 10 to the minus 4th in the trapezoidal rule, and you were iterating to 10 to the minus 8th in the Simpson's rule, but you had to iterate to 10 to the minus 12th in this rule. So I want those numbers compared of how long it took relative to the number of cycles to get these different requirements done. And I think you'll be surprised at just how well that Simpson's rule actually works. All right, good luck. And next time we're going to move on to differential equations in Chapter 7.